Hello, this is Christopher Angulo. Um, this is my project 2 for the DAT 301 class. Um, so, my project is on statistical regression analysis of judicial information and corporate misconduct in Zhengzhou City, China. So, this data I obtained from the Harvard Dataverse, and the first thing I did it was downloaded as an Excel. Is I went ahead and translated all these columns, and I did this using Word. So I copied this to Word and translated the columns. Um, and this is just Zhengzhou City. So that was the only change I did to the original Excel data file, so that then I can use it all in the same language for the project. And this is just a legend that I'll be referring back to for each column that was provided by the author of this data set. So, um, first thing I do is I import everything I'm going to need. NumPy pandas, matplotlib, stats, CP stats, sklearn, and stats models. Um, so here I go ahead and read the Excel file. Then I enable this matplotlib inline so that I can see the graphs here on the Jupyter. So this, I'll go ahead and introduce the study. This statistical analysis studies data of judicial informatization and corporate misconduct in Zhengzhou City in China. First, a possible relationship between profitability and judicial informati uh, judicial informatization of business in Central City is explored. So profitability in this data set depicts the net profit ratio over total assets of a company. The larger this ratio is, the more profitable such company is considered. And that's one column. Another column is the judicial informatization, um, which has to do with such company being within the jurisdiction of the Chinese Internet Court. Hence, the first exploration that we're going to do of this data set is an attempt to find any possible relationship between profitability of companies and such companies being under the jurisdiction of the Internet Court. So, the first thing we do here is grab the data where for the companies that are not within that jurisdiction. So this is going to filter out all the data. 0 in the database for jurisdiction means that it's not within the jurisdiction, and 1 means in this jurisdiction column, JUDINF, means that the company is within the jurisdiction of the Internet Court. So we go ahead and separate that data out. And then we create a box plot for companies that are for the profit, which is the ROA column, for the profitability for both the companies that are not under Internet Court jurisdiction and companies that are under Internet Court jurisdiction. So we're going to create two different box plots. Um, so here we go. Here is the box plot for companies outside of the Internet jurisdiction. And we're kind of just seeing the frequency. This one is it's gonna say 1 for both, but this is focusing on the data for the companies outside Internet jurisdiction, and we see this profit axis here, which is the y-axis in this case, kind of being between 0 and 1, the median. And we see this as well for companies within the Internet Court jurisdiction. So we don't see a large difference in terms of that. We do see a larger variance, it appears, here for the companies within the Internet jurisdiction. So this is just to kind of give us an idea to see if we can find any notable differences with profitability from both of these types of companies within Internet Court jurisdiction and outside the Internet Court jurisdiction. So observing the above box plots of profitability between companies within and outside of Internet Court jurisdiction, it is not evident that there is a distinction in profitability between companies within and outside the Internet Court jurisdiction. Now, normal distribution curves will be graphed for profitability of companies outside and within the Internet Court jurisdiction. First is the normal distribution curve of profitability for companies outside the Internet Court jurisdiction. So here we're gonna graph a normal distribution curve for the companies outside, for the profitability of companies outside of the Internet Court jurisdiction. So we go ahead and just label the profitability data for companies outside of the Internet Court jurisdiction. We calculate their mean, their standard deviation, and this way we can go ahead and make a normal curve of this data using the mean and the standard deviation as well. So here is that. So here we're seeing kind of the peak of this normal curve here. It's a little skewed, but we see that it's just as a box plot showed between 0 and 1, and the frequency that happens a little over 4 here. And now we do the same for companies within the Internet Court jurisdiction. So this is the exact same process, just for the profit of companies within the Internet Court jurisdiction. And again, we see that peak from 0 to 1, and also kind of a similar frequency. So then, by observing the two normal distribution curves above, there is still no visible relationship between profitability and Internet Court jurisdiction status for the companies in this data set, because they're kind of showing the same behavior. So we're not really seeing a difference of profitability between a company that is within Internet Court jurisdiction and outside of Internet Court jurisdiction. So a better way to determine if a variable has a strong correlation with another variable is by fitting the data of both of these independent variables to a linear regression model. So on y, two variables are being tested. So this is actually on x. So on x, two variables are being tested. The Internet Court jurisdiction. So Internet Court jurisdiction is going to be x, and profitability is going to be y, because we are attempting to say that based on the status of Internet Court jurisdiction, there may be some relationship that causes profitability to have a certain outcome. So here we do a simple linear regression model between these two variables. So again, here we're going to grab the data for all profits, and we're going to grab the data for companies within and outside Internet Court jurisdiction. So we're just grabbing all profit data and all status of internet court jurisdiction from the full data set. We go ahead and do a 1-degree polynomial fit. It uses the least squares method. So we have our x and our y that we input there. Then we go ahead and create a function that takes in x and returns an estimate for y. It's using simple linear regression. We only have one independent variable. We are going to go ahead and plot it. So we're going to plot this function. And we're also going to obtain a slope and an intercept just so we can also numerically show this model, an equation for it. So we're also going to display that equation as mentioned, and also display the r-squared value to help us determine the accuracy. So here we go. Let's go ahead and do that. Okay. No bueno. What happened? Batch 2 data. Oh, I think I skipped. Sorry about that. I believe I skipped running a cell. I'm gonna go ahead and run these very briefly. Just to make sure we have all the variables we need up to this point in the data. So this is where we were. Here we go. Okay, now it's working. So here is that linear regression. Now, because this is kind of a binomial type of distribution, our outcomes are only 0 and 1 for either being within or outside of this internet court jurisdiction. We have this huge space between data points in this scatter plot, but these are basically our profitability over here on the y-axis, and then our internet court jurisdiction status on the x-axis, which is either going to be a 0 or a 1. And we see this as our linear regression fit line right here, this dashed line. So it doesn't look too well in this type of data, but this is what we have. And this is the equation for it. And it has a very low R squared score. So that kind of tells us typically R squared is going to be used to determine if this is a good approximation, a good linear regression model, and a low R squared is going to tell us that it probably is not. But R squared also takes into account the amount of variance between data, and here the variance is pretty huge. It's a big space here, so that could also be a cause for making it such a low R squared. So one observation from the SLR, which is the simple linear regression model above, is that a company within the jurisdiction of an internet court has a slight decrease in revenue. It's going a little down. So as we get to being in the internet court jurisdiction, we do see that it decreases, that profit decreases a bit. Also, on this SLR model above, the R-squared score of the model is very low, so this may provoke a hypothesis that states that this SLR is most likely not a good prediction model. However, an R-squared score is not the only factor that explains how good of a prediction model this SLR is. A more important value to consider from this SLR model is the p-value of the independent variable. The independent variable in this case is that internet court jurisdiction status. Below is a detailed summary of this SLR model, including the p-value of the independent variable, the internet court jurisdiction status. So we go ahead and create a linear regression model using the stat model library in Python. So here it is, and we go ahead and print out the summary. So this is doing the same interpretation of this linear regression model equation, but it's just going to allow us to print a summary of it, a detailed summary. So here is that summary. And what we're looking for now, we already know the R square is very low. It kind of rounds off to 0.02, right? 0.019 rounds off to 0.02. But what we're looking for is a p-value now. Now, here are the p-values. The p-value that we're interested in is for the independent variable, not the constant. Here's the independent variable, JUDINF 0.036. Now, the way Python is doing this at the moment, these simple linear regression models, is using a 95% confidence interval, which means we have a significance level of 0.05%. And I'll go ahead and let this explain this. So this writing here, this SLR model uses 95% confidence interval, aka a 5% significance level, alpha equals 0.05. To reject the null hypothesis of this SLR, the condition that its p-value is less than a must be met. If we do reject the null hypothesis, this is going to mean that the SLR model holds a significant statistical value of prediction between independent and the dependent variable in the model. So if we are able to reject the null hypothesis, which is if we're able to meet this statement here as true, then that means that this model actually is pretty statistically significant. Observing the p-value of the JUDINF, which is the status of internet jurisdiction, 0.036 is the p-value. It is 0.036. Comparing the JUDINF p-value to the significance level, which we said is 0.05, we see is 0.036 less than 0.05. It is. So we are able to reject our null hypothesis, and this signals that this simple linear regression model is actually statistically significant. So we can't just go based off the R squared, because now with this hypothesis test, we're seeing that it actually looks like this is a significant linear regression model, as weird as it looks. So next, an exploration of all Bernoulli type variables, being that it's either a yes or a no, and being in the internet court jurisdiction in the dataset, are analyzed in an attempt to search for even more variables. So now that we know that at least one variable is significant, we're going to try to search through more variables that are similar Bernoulli type variables of either yes or no within the data set that may be able to predict the profitability values. So the rest of these variables that are Bernoulli type variables are going to be MISC C1, which is corporate misconduct, infringement, internet infringement dispute, MISC C2, which is internet contractual breaches. JUDINF, we're going to include it there anyways and redo it with this data again, even though we know it's significant. Judicial information, media attention IC, internet controls, dual, CEO chair duality, and SOE state ownership. So these are all different variables. Here is the key for them. Now we're gonna see if any of these help us also be able to predict profitability. Let's see if they are statistically significant in that manner. We're gonna go ahead and generate data similarly as before, but this time our X is gonna be multiple columns. So instead of using a simple linear regression, we're gonna do a multiple linear regression because it's gonna have multiple independent values, which are all of these, and this is our Y, our dependent, which is the profit. So we go ahead and use this MLR model again, but we need to create a constant for it. It just this is what it in default stats model doesn't have a constant, so we need to make it. Then we go ahead and print out the summary of this. We're not going to graph yet. First, we want to now that we know that this p-value is more significant at determining this statistical significance, we're just going to look for p-values that meet this that are able to reject the null. That means that they're statistically significant. So we don't need the constant, but we are going to check all of these, and we're going to check that they're less than 0.05. So for example, this one is not, we ignore it. This one is not, we ignore it. This one again, JudeInf, it is, so we keep it there. Media is not, it's over 0.05. This one is not. Dual is, SOE is not. So it looks like only two variables are significant, statistically significant. So the multiple linear regression model above provides p-value calculations for each independent variable. This MLR model is computed with a 95% confidence interval. Hence, independent variables with a p-value less than A are considered statistically significant. All other independent variables with a p-value more than A are discarded as statistically insignificant. After this, a new MLR model is ran without the previously identified statistically insignificant variables. So we're going to rerun the model, but we're going to only grab the variables that we found statistically significant, which again is what we had already found to be statistically significant, JudeInf. And now this additional dual variable, dual is means CEO chair duality, where the chairman and CEO are the same person. So we're gonna see if the status of that of a company also affects profitability. If there's a strong correlation there. So again, we're gonna go ahead and run this multiple linear regression model again, and let's look at its summary now. So now we only have these two, and we are seeing that indeed they are both less than 0.05. These seem like the two variables that are pretty significant in affecting the outcome of the profitability. Okay, so observing the p-values of both JudeInf and dual independent variables, you can confirm that these two contain statistically significant p-values. They're both less than A. They're both aka 0.05. It is now clear that a statistically significant MLR model has been created. It is not very practical to model all three variables, two independent and one dependent, in a plot, but hey, we're going to do it anyways in a 3D plot and take a look at it. So here, we're just going to grab the parameters of the coefficients, which are these values. These are basically our betas. We have our beta naught, which is the coefficient, and our beta 1, beta 2 of the linear regression model. So we're going to go ahead and grab them. And here it is, beta naught, beta 1, beta 2. Grab their values, and we're going to plot them in a 3D plot. So this is all just creating the plot. Let's go ahead and take a look at it. Doesn't look very helpful. We have our profit up here, our ROA. We have our dual chair, CEO chair duality status, and our internet court jurisdiction status. And yeah, not very helpful. So the above 3D linear multiple linear regression model plot contains judicial, dual, and ROA axis, as we mentioned, and the color is linked to the profitability, the ROA. So the higher it goes, the brighter it is. It starts from dark purple to bright yellow. So we need a better way to graph this. So what we're gonna do is we're gonna, instead of graphing a multiple linear regression model, we're gonna graph two simple linear regression models. So two scatter plots with a fit line. One is gonna be for the combination of one independent variable with the dependent variable, and then the other independent variable with the dependent variable, which is the same dependent variable for both. So here we go. First, we're gonna graph the scatter plot of the SLR best fit line of the judicial uh, internet court status and the profitability. So here it is, and this is what we see. And this above scatter plot is actually the same scatter plot. It's the same data that we presented near the beginning of the analysis, if you remember. Here, however, we derived this model from a multiple linear regression model that we made right now, right? But yeah, this is what we see, and then we're gonna do this for also the chair CEO duality and profit, and we see this. We actually see a positive. Uh, this 3D model is a combination of this and this is what we can kind of see. But these graphs allow us to get a better sense. It's kind of telling us that the status of internet jurisdiction decreases profitability when a company is within that status. When it's not, it actually increases profitability slightly. And we also see that if a CEO is both the if a person is both the CEO and the chair of that company, it increases profitability slightly. And if it's not the same person as the chair and the CEO of a company, profitability decreases slightly. So then we merge these two things together to kind of create this outcome. So, in summary, these findings of this statistical analysis suggest that for businesses in Zhengzhou City, China, the status of being in an internet court jurisdiction slightly decreases profitability, while the existence of a CEO chair duality for a company slightly increases profitability. These decreases in decreases in profitability due to internet court jurisdiction status and CEO chair duality status are statistically significant for a multiple linear regression model of the data. But again, they're very slight, right? It's not a strong slope, not steep. And this is my bibliography. Author was Jean Li, and it was retrieved from the Harvard Dataverse. Thank you.